Hi Year 12. Here's our fourth lesson for the topic of further integration. In this lesson we're going to look at integration by parts. So far we've revised integration methods, T-ratio substitutions and partial fractions. Now a useful integration technique is integration by parts, and it involves this formula. Have a quick look at it. On your reference sheet it's going to look like this, but it's exactly the same. Instead of v dash they've written dvdx, and similarly over here. It's going to involve a product of some description. One part that you're going to differentiate and the other part that you're going to integrate. Now the proof of this formula is really simple. It just comes from the product rule. Here's the product rule, and if we make this the subject, we get this, and integrating both sides, we end up with the formula. Integral of this is equal to, we do the integral of a derivative, they cancel each other out, so we just end up with uv, take away the integral of this. So that's where the formula comes from. Now it's particularly effective when we have an integrand that contains a mixture of algebraic, trigonometric, logarithmic or exponential parts, like these two. So here I've got an exponential multiplied by a trig function. Here I've got an algebraic function multiplied by a logarithmic function. Now here's the method. Split the integrand into two parts. We're going to put one part equal to u and the other part equal to the derivative of v. Now here's an important point. Choose carefully, otherwise the integrand can become more complicated. Here's our first example. Find the integral of x e to the x dx. So we definitely do have a product. We've got two things here, and we're going to make u equal to x and v dash equal to e to the x. Now one of the reasons that I've chosen that is because when I differentiate x, I'm going to get 1 and this is going to disappear, which is going to be helpful to me. So we're going to write it out like this. U is equal to x, v dash is equal to e to the x. Differentiate this gives us 1. Integrating this gives us e to the x, and we're ready to substitute into the formula, which is here. So it's going to equal u times v. So u times v is x times e to the x. Take away the integral of u dashed multiplied by v, which is just e to the x. And you can see how the x has disappeared. And now we can integrate this. So it's just going to be equals x e to the x, take away e to the x plus c. Example 2. Use integration by parts to find the integral of ln x dx. And this one's a bit strange, isn't it? Because we don't have a product. We've only got one function. So this is the method we're going to use. It's a bit of a trick. We're going to put it equal to the integral of 1 multiplied by ln x dx. And we're going to make v dashed equal to 1 and u equal to ln x. The reason we're doing that is because we can't integrate this. We can only differentiate it. So let's write it out. U is equal to ln x, v dash is equal to 1. The derivative of ln x is 1 on x, and the antiderivative of 1 is x. Now let's put it into the formula. So we've got u times v, which goes here, take away u dashed multiplied by v, which gives us 1 on x times x, and that's actually only 1. So we want the integral of 1 here. So our answer is going to be x ln x take away x plus c. Example 3. Find the integral of x ln x. This one's very similar. We're going to let u equal ln x just like we did before, and v dashed equal x. And so this is going to become 1 on x, and when we integrate this we get x squared on 2. Okay, into the formula we need u times v, which is x squared ln x on 2, take away the integral of 1 on x times x squared on 2. Now tidying this all up, we're going to get x on 2, which is a very easy thing to integrate. It is x squared divided by 2, and of course we've got a 2 on the bottom, so it's going to become a 4 on the bottom. So you can see how simple this is if you choose correctly in the first place. Now sometimes we need to perform integration by parts more than once to get the answer. Like this, integral of x squared cos x dx. So see, if I make u equal to x squared and v dash equal to cos x, then when I do the derivative of this I get 2x, which isn't really going to help me. Using the formula we're going to end up with u times v, which is x squared times sine x, take away, and then we've got the integral of 2x times sine x. So we're going to do it again. we're going to do integration by parts on this, and that x will then reduce to 1. Like this. So here I'm going to say that u is equal to x and v dash is equal to sine x. So derivative of x is 1. Integral of sine x is negative cos x. And now let's apply the formula just on this part here. This gives us this, and now you can see we've got something that we actually can integrate. And so that stays as x squared sine x plus 2x cos x. Take away 2, the integral of cos x, which is negative 2 sine x, and then of course our constant. You saw in the previous example how we had an x squared term that reduced to an x that reduced to a 1, and that's the way we were able to eventually find the integral. We also have recurring integrals, like this one. If you have a look here, this e to the x term is never reducing down, it's going to stay the same. And the sine, it oscillates between sine, then cos, then back to sine, then to cos, then back to sine. And we can use this recurring nature to our advantage. I'll show you what I mean. We're going to let u equal e to the x and v dashed equals sine x. The derivative of e to the x is e to the x. The antiderivative of sine x is negative cos x. And let's put that in the formula. Now I am going to let this integral equal capital I, and I'll show you why that is in a minute. Okay, so there's our question. There's our first application of integration by parts. U times v, take away the integral of u dashed times v. Okay, and you can see how e to the x is still there, sine has become cos, but we're no closer to an answer. So I'm going to do it again. This time I'm concentrating on this integral, and again I'm going to let u equal e to the x and v dashed equal cos x. Here's the derivative of e to the x, here's the antiderivative of cos x. All right, substituting in, and I'm going to get this. This is u times v, take away the integral of u dashed v dx. All right, what can you see? This is actually I. Okay, it was the same as we started with. So let's make that substitution. Now let's take the I over the other side to join with this one. So 2I is equal to, I have factorized these two terms and switched them around. E to the x and then bracket sine x, take away cos x, divide by 2, and we have the answer. And that leads us nicely into our next lesson, which is on recurrence relations.